Okay, hopefully you see that if I add this dimension plus this, plus this, plus this, plus this, plus that, it equals the length of the curve. So when you add all these up, they better add up to the length of the curve or you mess something up. Okay? And they do. I did it. Okay, the next is the distance from the beginning to each stake. So the first one is from here to the first stake. Second one is the beginning to the second stake, beginning third stake, beginning fourth stake, and so on. So all I got to do is use this as my tally. Start out 15. 15 plus 25 is 40. 40 plus 11 is 51.39. Okay. 51.39 plus this is 65. 65 plus 25 is 90. And 90 plus 12, 78 is 102.78. And that should look like something that you've already calculated. That's the length of the curve, which makes sense. From the beginning to the end is 102.78, and that is the length of the curve. So there's your L's and delta L's. Okay, from there, we're going to move on to a calculation. This delta L is that column. This L is that column. So if I have a D, all I'm going to do is multiply it by that, and that gives me the deflection angle. D is the unit deflection angle, the number of feet of arc, or the number of degrees of arc per foot of arc. So D is as simple as this. D is a unitized deflection angle. So I want the angle on top, I over 2. That's the biggest angle I can do is I over 2. And I'm going to divide that by the length of the curve. That'll give me the number of degrees per lineal foot. So I over 2 divided by L. In my case, that came out to this 18.4027 and 102.78. Okay, here, you've got to carry this out to multiple digits. If you round it off, you're going to get data that doesn't work. So carry it out quite a ways, and I carried it out about, a lot. I've carried it out a lot. Here's what I got. 0.1790501.826 degrees per foot of arc. That's my constant. Okay, I take that constant. So every time I move a foot on this arc, I have turned the transit 0.179 degrees. Okay, so if I take that and bring it over here and put D right up above here, 0.1790501.826. He goes here, and he goes there, and I multiply it by these numbers, I get the number of degrees that I'm turning the gun. So I did it, and I'm not going to waste a lot of your time, so I got this one as 0 and 0. That's right on the line. That makes sense. 2.68. 2.68575. 4 point. 2 point. 2 point. 4 point. Notice Those are the same. Why? Because they've got the same length of arc. And the last one, okay, if I add all of those up, I'm going to end up with I over 2. So the sum of these has to equal I over 2. So what is that angle? Let me explain what it is. I'm going to get rid of this guy. We already know what he is. Okay, I'm sitting my gun. I'm going to look at these stakes. So here's my first. Here's my second. There's my third. There's my fourth. There's my fifth. And there's my sixth. Okay, that angle that I just calculated, okay, is the incremental deflection angle. It is the angles right here. Those are the D times delta L's. They're the angle between adjacent lines going to specified stations. Okay? So if I turned the first one, I would turn 2.68 degrees. Then if I went from that line to the next line, I'd have to go 4.5 more degrees. To the next line, about little over 2 degrees. About 2.5 degrees, about 4.5 degrees, and then finish off with 2.3. So that's the incremental. Okay, difference between that line and the next. Next line is this. I'm going to use a brown one here. The first one's the same. Second one is here. Third one is here. Fourth one is here. Fifth one is here, and sixth one is here. So these are DL. They're the angle from the tangent line to each of the stakes. So they're the summation, the aggregate deflection angle. So if we go over here and I fill this in, it looks like this. 0 stays the same. 2.68575. This plus this is the next one. And that came out to 76162, 7.162007. The next one is this plus this, 9.20. Next one, this plus this. Next one, this plus this. And the last one, notice how that relates to this number and this number. The sum of these is I over 2, which is that number. The angle between the beginning and the end is I over 2, which is this number. That is the same as I over 2 over here. So if I wanted that next to last angle right here, I would turn 16.114516. So on my calculator, I could put 16.114516. Convert degrees, minutes, seconds. I would be turning an angle of 16 degrees, 6 minutes, 52 seconds. So we got to convert back and forth. That's why we had those problems on your first test, so you understood how to go back and forth. Now, the last two columns, difference. Okay, those brown, the brown arrows go to long green lines. Okay? Those long green lines are long chords. So all of these guys Now don't confuse that with the long chord. The long chord is right here. These are individual long chords to each stake. So the long chord is the distance from the gun to the stake. Okay, the short chord is the distance between adjacent stakes. So a short chord is this distance right here. So I can go around it like that. These are all short chords. The long chord is from the gun to the stake. Most of the time we'll be dealing with the long chords. So how do we get them? Well, you had an equation not too long ago, and that equation is used here. It's a long chord equation. So the short chord equation looks like this. 2r sine of the deflection angle over 2. That's d times delta L over 2. Okay, so when I do that, let me make sure I've got this right. Long chord, short chord. Did I do them? I did them. Okay, short chord. Let me do the first one and make sure I've got this right. I would take delta L and multiply it by the sine of this guy right here. So this angle goes right here. And 2r, r was written down before, and that was 160. So r is 160 feet. So the 160 goes right in here. So if I take 2 times 160, 2 times 160 times the sine of 2.68575 divided by 2, multiply the 2. Actually, it's not divided by 2. It's d, that's what I was afraid of, d delta L. That angle, don't divide it by 2. It's already divided by 2. Okay, so 2 times the 160 times the sine of 2.68575 gives me 14.995. 14.995. Okay, I move down to the second one. 2 times 160 times the sine of 4.476254 gives me 24.975. 24.975. And I just keep going. And I've already done it, so I'll fill them in for you. That one's there. This is 11.388. And this is 13.606. And this is 24.975. And the last one is 12.777. So if I measured from here to here, that would be 12.78. If I measured from here to here on a straight line, it would be 24.98. Okay, makes sense. The straight line is shorter than the arc. Now the last one is the same equation, except the long chord is equal to 2r sine of d times L. And d times L is these numbers. So I'll do the first one, then we'll write the answers in for the rest. R is 160 yet. So it's going to be first long chord I did, they're the same. I'll do the second one. 2 times 160 times the sine of 7.16200, and I get 39.896. One more. 2 times 160 times the sine of 9.201388, 51.170. And you just keep going right down the list. And if I did this right, I got these numbers: 64.554, 88.819, and 101.022. And a little bit of a check. Are these a little smaller? Yes. Yes. And yes. And does this number look familiar? You calculated a little while ago, it's the long chord length. I'm sitting here, I'm looking right down this line, and that in fact is the length of the long chord. So you got to go step by step. This is the table you'll be developing. I'll give you a sample problem. It'll be a little bit larger than this as far as diameter. It's going to get bigger, so you're going to have a longer arc. Your job is to figure out a way using Excel to generate this table. And when you do that, of course, you're going to end up being able to put that in there. You're going to have to find something to develop a way of determining D. You have to put some logic in there to fill in these two lines given these stations. So those stations you are actually going to physically put into the program. This should be a byproduct of this line. So should this. If you've got D calculated somewhere, you can multiply that by these values to get this column and this column. And then you're going to have to embed the equations into this and grab the data to generate that and make sure you do your checks. So when you get done, the only real data you're going to input is going to be, look at what we've got. Each station, to put that in, you have to put the length of the curve in. You're going to have to put I over 2 in. So the length of the curve and I over 2 are a must. You got to put that in as a number. And then from there on, I think the rest of it is just let the program